Okay, so there's an app which I'd recommend you have a look at to play with this idea a little bit. So here's the link for it. And so what you do is you choose the distribution up the top you're going to start with. Then you get some sample data, and it will show you what the mean looks like. I've set it up to give me the mean of 5 observations and the mean of 25 observations. So here we go. I've taken a sample of size 5. That gives me a mean. And then I'll take another sample of size 25. And that will give me another mean of 25 observations. Okay, and so then I could do that again. And I could do it again and again and again and again and again and again to look at what the histogram looks like. To look at the sampling distribution. The sampling distribution of a mean of 5 observations or the sampling distribution of a mean of 25 observations. So I'm going to do that. I'm going to save you the animation, just show you what it looks like if you do a whole heap of them. There it is. If you start off with a normal distribution, average 5 observations, it's normal, but with a smaller standard error because of this divided by root n. Do it for 25 observations, it's still normally distributed, but even smaller again. Now we knew that from before, we worked that one out before. What happens if I change this to a different distribution? I'm going to use a uniform distribution. It's equally likely to take any value between there and there. For 5 observations, averaging 5 observations, it's approximately normal. It gets even better if you're averaging 25. Okay, what if I use different distribution again? What if I use like a skewed distribution? Like that one. See how that's not normally distributed. It's a right-tailed distribution. It's usually generating a value down here. Sometimes occasionally you get quite a high value. What happens there? It's still approximately normal. The sampling distribution of an average is still approximately normal by the central limit theorem. You can see, if you look carefully, you can see that after 5 observations it's still a bit right skewed, but by 25, it's all over. Okay, I'm going to make up my own distribution now. I'm going to go like this. I'm going to go up, I'm going to go down, go up, and go down again. See what this does. That's a weird distribution, isn't it? That's clearly not normally distributed, this data set. Data from this distribution is clearly not going to be normally distributed, is it? So, I'll sometimes get one down there, sometimes get one up there. All right? So this is called a bimodal distribution, something with 2 peaks. So the data's usually here or here, and it's not often in the middle. What happens if I sample from this distribution lots of times? The average is approximately normal. This theorem works pretty well. Even if you're averaging 5 observations, it seems to work pretty well, doesn't it? But yeah, by the time you're averaging 25 observations, it's really hard to beat this thing. It's really hard to beat it. Have a play around, see if you can find a distribution that beats it. You'll struggle. You'll struggle because like this theorem, it actually it works quite well at surprisingly small sample sizes. So, I guess in terms of thinking about how well it works, people often say if your sample size is bigger than 30, then the central limit theorem will probably work for you. Strictly speaking, it is possible to find a distribution for which a central limit theorem doesn't work at any sample size. You can always sort of do some tricky stuff to find something that's a problem for it. But for most distributions you'll see in practice, at sample sizes 30 is fine. The things that cause specific trouble for the central limit theorem, and you can see that in the proof, like something that's useful about the proof, if you work through the proof of the central limit theorem, that video. When you look at the form of the proof, you can see what sort of distributions will cause an issue. Skewed distributions and long-tailed distributions, ones with outliers, big outliers. They're the ones that the central limit theorem has a harder time with. If you're sampling data that's really strongly skewed and occasionally has really big outliers, then the central limit theorem won't work as well, and you would need a larger sample size in order to say your average is approximately normal. You would need a bigger sample size for a skewed or long-tailed distribution. So if you look at your data and you see it's not that skewed, sample size of 30 is plenty in order to be able to say that the average from a random sample is approximately normal. If it is skewed or long-tailed, then maybe you should be doing something else. Averages aren't very helpful in those situations anyway, as measures of centre. You could try transforming your data, for example. I guess there's something else that's worth mentioning with the central limit theorem. Like there's some variables that you see in practice which seem to magically look approximately normally distributed, and one reason for that is that if you're measuring a variable which you can think of as the outcome of a bunch of processes that have been added together. Height, for example, you can think of height as you were this big, and then you grew this much, then you grew this much, then you grew this much. So it's this plus this plus this plus this plus this. You can think of that as like a sum. The central limit theorem says sums and averages are approximately normal. And so like height, so that's one reason why we might look at a variable like height and not be overly surprised that it's approximately normal. But the main goal, the main reason why the central limit theorem is important isn't so much because it explains why some data that you observe as normal. It's more because statistics we're interested in. Statistics that we want to calculate from data are often normally distributed. So then we can use this to say stuff about the true mean.